Okay, so let's look at some bolts. So bolts are useful. Uh, Easy and quick disassembly is primary benefit there. We are able to, ship stuff out in smaller packages, bolt stuff together, um, remove stuff for maintenance, remove stuff for, if it needs repair, or if, maybe you just need to get it out of the way of something else that needs maintenance, so on and so forth. Uh, Bolts are standard machine elements, readily available. Unless you are working for a bolt manufacturer, it is almost always going to be more beneficial for you to purchase bolts and use them than to try to make them yourself. So, yeah, the loads are applied to the structure. The structure is going to have a tendency to say want to separate, and the bolts are going to be preventing that separation. So the load gets transmitted through the rest of the structure to the bolts. They become stressed. Um, and then if the joint fails, obviously the structure itself can be considered as failing. So you want to basically design them in a manner that you are using large enough, strong enough bolts, what sort of tightening load you need to apply them to, so you can operate without failure. For some instances, it's not just the bolt failing itself that would be a problem, but it also needs to stay tight enough. You can't have any leaks going on. That would also constitute failure. So when we're designing, we're for this course, we're basically going to kind of be assuming a certain type of bolt, and if you want to be using a different type, then that'll kind of be beyond the. You can use the same analysis that we've provided here to kind of do that. But you're going to need a certain number and distribution of them. How big is the bolt going to be? How tight do you need to make it to begin with? So what sort of initial tension or initial tightening torque do you want? So a bit of nomenclature. So uh, screws into a threaded um, threaded joint here. So typically speaking, versus a bolt, it connects it holds stuff together via a nut. Oftentimes a washer. Typically speaking, the if something is designed to be used as a bolt versus a screw, then it's going to usually have a a smaller threaded section, but it's not always the case. Get a stud and nut. So basically, this is a kind of double-sided threaded portion. So you can just screw the stud in to the threaded portion until it kind of hits the non-threaded portion, goes as far as you can, and then you apply the nut on top of that and apply the tensioning via that. So here's a couple examples. I got threaded rods too, so it's basically just threaded all the way through, and then you tighten the tighten nuts on either side as well. So some general geometric characteristics. Let's see here. Come on, cooperate with me. There we go. So we got the few important things. Nominal diameter and the pitch is usually what you're going to be using to define a standard bolt. So the nominal diameter is just kind of from the center, from the outside edges of the threaded portions. We've got the pitch, and that is just the distance between kind of the same section of the bolt. So it can be measured from here to here, or it could be measured from here to here, or it could be measured from here to here. Same deal. Should be the same thing. Got the pitch diameter. That's basically the diameter kind of halfway through the slanted portion here. Got the root diameter. So that's the diameter based upon measuring from the inner portion of the threads there. So like I said, bolts are going to be coming kind of in standard configurations. So like for example, an isometric bolt, it's going to be represented by the nominal diameter. So again, that's this one here, and the pitch. Both of those will be in millimeters. And then all these other values, like the pitch angle here, and the root diameter, and the pitch diameter, and like the size of that there, that'll kind of be specified as a result of kind of as functions of those two of the nominal diameter and the pitch. So that having said, we still need to we need to have certain we need to take those pitches and those diameters and figure out what's certain parameters that kind of go to the. So the stress area is an important one. So the stress area. Okay, so if you got a threaded portion, actually here. Okay, so if we look at this is kind of a bit of an exaggerated view, but if we look at this, so obviously, if we look at a thread, then along the center line here, on one side of the on one side you're going to have kind of the threaded portion, and then kind of on the other side of the bolt you're going to have the root at the same portion. That's going to kind of result in a certain cross section that has the smallest area on which you can have failure. So it's going to be kind of based upon kind of a bit of a slanted area that looks like this. Kind of, so based upon kind of the combination of what sort of pitches you're using and the diameter you're using, that's going to lead to a certain stress area. That stress area is kind of where that's the kind of the slanted area across which we're going to have the smallest cross-sectional area, and that'll be basically kind of where we're the area which we're going to be using for our calculations to determine where we expect failure to occur. So it's going to be based upon whether or not what the diameter is, what the pitch is, and also whether or not we're working with coarse or fine threads. Typically speaking, coarse threads will be there's kind of like standard coarse threads and standard fine threads and standard extra fine threads for a particular diameter. So each of those diameters will be associated with a particular pitch for coarse threads and a different pitch for fine threads, and that's going to result in a different stress area as well. So relative to the size, the coarse threads, because they basically because they're bigger, they're doing this instead of, say, this. It's they're kind of carving in deeper. You're getting more more material removed, basically, when you're machining threads, or you're not always machining, you're often rolling, but that's neither here nor there. But anyways, so the coarse threads version is going to have a smaller stress area than the fine threads version. That having been said, oftentimes the threads themselves, because they're larger, will basically uh, may have a bit of a higher load carrying capacity. The failure isn't always just kind of through the bolt, it can be also on the threads themselves. So we want to kind of take those into account too. So yeah, here's just some more examples for typical pitches and stress areas. So there's a whole bunch of standards that kind of have arisen. Some are more popular than others, but the kind of got the English system, UNC, UNF, UNEF, Unified National, coarse, fine, and extra fine. So those are going to be specified by giving the diameter, the pitch, the type, and then we got some other stuff here. So the fit, I'm supposed to say external, and then the directionality. So this is a three-quarters of an inch diameter, three-quarters of an inch diameter bolt with 10 threads per inch. Unlike the metric system, the UN specification system gives threads per inch, so it's like the inverse of the distance between the threads versus giving the pitch in diameters. Coarse or fine. Fit type, so high precision, low precision, medium precision. This is the middle for 2. ACE or external, so again this is a bolt, not a nut. And then right hand. So here's a few examples of kind of what we can see. So different sizes. For smaller stuff, they give numbers. So like a number 2 bolt, a number 10 bolt, so on and so forth. That kind of goes all the way up to 12. And then after that, we start specifying it by the kind of actual nominal size. So a quarter of an inch is kind of the first standard size bolt that wouldn't be specified with just the number. And of course, this can get confusing if you don't know which one you're talking about. Like if you're talking a number 1 bolt versus a 1-inch bolt. So don't forget to omit the number or the inch indicator, because otherwise you're talking substantially different sized components there. So again, a standard coarse thread versus a standard fine thread. Each of the diameters that you're working with will have kind of like a standardized type of number of threads per inch for coarse and for fine. So for example, for the coarse, we're looking at 13 threads per inch for a half-inch bolt, whereas for the fine, we're looking at 20 threads per inch for a half-inch bolt. And then that results in a different inner diameter, so like that's the root, and in a different tensile stress area. So, we're looking at 0.1419 inches squared for the stress area for coarse bolt, half-inch coarse bolt, and we're looking at 1.599 inches squared for the same size in a fine thread. Oh yeah, just need to look up the stress areas on our table. And again, this is all found in juveniles. All these standard sized for particular threads per inch. So for the strength, again, we're looking at kind of two different tables, whether or not we're talking the English system or metric. So for the English system, we're given basically grades. So 1 through 8, and those correspond to kind of certain grades will come in certain diameters, and those will have certain yield strengths, ultimate tensile strengths, hardnesses based upon different tests, and proof loads, and we'll talk about proof loads in a second. And then some of them will have different markings on the bolt head in order to indicate, to tell you what sort of grade we're talking about. So proof load. Proof load is basically telling us what sort of load we can apply to a bolt before you get permanent deformation of 0.0001 inches. Again, this is measured on actual bolts. So this is not kind of a calculated one. This is experimental data. So it is, basically, this is kind of like a more stringent version of what we would typically talk about yield strength, where we're talking 0.2% offset on a machine test specimen. So proof load, we're again, if we're looking at our kind of just a tensile test, we got going to have a certain area where it's going to be still linear. So basically, proof load, we're kind of more closer to the curve versus maybe yield strength is something like this. So it could still be fairly close in terms of strength levels. For example here, for a grade 5 bolt, for a grade 5 bolt for 1/4 inch through 1 inch, proof load we're looking at 85 KSI, yield strength 92 KSI. So again, same ballpark, and of course, and that's still a fair bit off before you expect failure. And then the classes that we have associated with for metric systems, those are kind of indicated. Those have decimals associated with them, so that's kind of how you can tell the difference between the two. And again, certain diameter ranges. and then proof strength, proof load, and yield strength and tensile strength still given. For the proof load, corresponding to permanent deformation of not over 0.0025 millimeters, which again is basically equivalent to the definition. Oh, sorry, I guess, which is basically equivalent to the definition of the proof load for the imperial system, 0.0001 inch. When you take that 0.0001 inch, multiply it by the 25.4 inches, millimeters per inch, that's what you get in millimeters. I know that they dropped the 4, whatever, no big deal. So, generally speaking, we're usually looking at about 0.96 of the yield strength. But if you have the actual experimental data to work with, then it's do so. Now here's just an example of the mechanism that would be used to test said bolt strength. So as for sizing, so we need to determine a few things. So we need to determine our initial tensioning. So how tightly do we need to clamp together this joint? So the initial tensioning is going to cause a certain amount of force, and that can be determined as basically, and that's going to cause a certain amount of stress level in our threaded area. And that stress level that's caused could be considered as a portion of the proof strength. So typically speaking, you're going to want to be loading up your bolts to between 3/4 and 100% of your proof strength. A value of 0.9 is reasonable. For most applications, you want to be making these tight. You want to be making them fairly close to your proof strength, because and the point of bolts is to maintain a nice tight connection that holds your joint together. So as a result, you're going to need to tighten up tighten up either side in order to allow for that initial tightening, that Fi, that corresponds to that particular portion of the proof strength. That having been said, it can be difficult to measure this. You can rotate it, you can tighten it up a certain amount, you can rotate, but you might be able to estimate it, but precise measurement, you may need to use some sort of strain gauge or ultrasonic measurement to get it if it is critical. So here's an example of a bolted connection where they're using an ultrasonic measurement in order to determine with fairly good accuracy whether or not it's been tightened up to the amount it needs to be. Here's an example of a bolt that has an axial strain gauge implanted in it, so that allows precise measurement of exactly how much you tightened it up to. Having said, most of the time we don't bother with that, so we use a torque wrench. So it gives a reasonably accurate estimate of how much reasonably accurate estimate of how much you tightened it up to. Again, plus or minus 15 to 30%. May or may not be suitable for your applications. You may have over tightened it a little bit, so you may be bit beyond the proof strength. You may have actually caused a bit of permanent deformation. Probably not the end of the world, but but in general, the torque that you apply can be used to estimate the initial tightening based upon this relationship. So you can solve for the if you apply a certain amount of torque. If we want to solve for Fi, then Fi would be equal to the torque applied divided by 0.2 d. So where d is the nominal diameter of the bolt. If you're using oiled or grease threads, then less torque needs to be applied in order to tighten it up. So just keep that in mind as well. So as for what's going on, so we are going to have a certain amount of load distributed here. And so when you're at here, when you first apply the bolt, you insert the bolt through the bolt hole, throw the nut on. Before you tighten it up, you're left with a certain amount of distance. So like the distance in the shank here between the head of the bolt and where the nut is set, that is initially going to be just the thickness combined of the two members that you're tightening together, or the two or more members that you're tightening together. And then you're going to be tightening it up, and you're going to be basically clamping down. So you're going to be clamping down, you're going to be applying force. The head of the nut and the head and the nut are going to be applying force on the joint. Those two things are going to be compressed, and thanks to Newton's third law, the joint is going to be pushing back, and that's going to cause some stretching in the bolt itself. So you're going to get a certain amount of force in the bolt and a certain amount of force of compression in the joint. And that is going to lead to a certain amount of stretching of the bolt and a certain amount of compression in the joint based upon the relative stiffnesses of those two. So what is the Young's modulus of the bolt? What is the Young's modulus of the materials that are being bolted together? What are the cross-sectional area? What's the cross-sectional area of the bolt? What's the effective cross-sectional area of the joint? And of course, that's going to, at any particular point, the force in the bolt needs to be equal to the force in the not at any particular point. When you're first tightening up, before any other external load is applied, the force in the bolt needs to be equal to the force, the compressive force in the joint. So that's what we call our Fi. Otherwise, we are not in equilibrium, and I don't know, and essentially it's gonna have to settle out. So we apply that, and then after that, we're typically going to be applying some sort of external load, because what's the point of bolting together these two parts if there's nothing that's going to be trying to pull them apart in the first place? So when we apply some sort of external load, then basically that's going to cause a certain change in the loads in the bolt and in the loads in the joint. So what's going to happen is when you apply that external when you try to stretch it apart, what's going to happen is you're going to increase the tension in the bolt and you're going to decrease the compression in the joint. And then you add those two things up and it equals to the magnitude of the external load. So how does that get distributed? Well, that depends upon kind of the relative stiffnesses. So you're going to get a certain amount of it going towards the bolt, and you're going to get a certain amount of it going towards the decrease in the compression of the joint. So you're going to end up with a new compatibility condition because, again, the bolt itself is going to stretch out a bit, and the joint is going to be, it's not going to stretch out, it's going to be compressed less. And then overall, there's going to be the combination of those two things is going to lead to the joint overall kind of increasing in its amount of displacement. So when we apply that, we apply this force, we apply that force, and that force is going to cause a certain amount of displacement, and those displacements are the same, right? Because we're stretching, so the bolt needs, we're stretching the joint itself, so the bolt needs to stretch by a certain amount, and that same amount of stretch that the bolt has is going to be the same amount of decrease in the compression of the joint. So the joint's going to jointed materials themselves are going to be compressed less, and the bolt's going to be stretched out more, and that's going to be that certain amount of displacement. So again, that's kind of like the extra displacement that's added from the initial equilibrium condition. And then the amount of force that's used to cause that displacement is based upon the stiffness of the bolt, which we're going to call KB, and the stiffness of the joint, KC. So the effect that has on the load of the bolt is based upon the initial, our new load on the bolt is based upon the initial load plus the KB times that delta. But again, we know that the delta, based upon our previous equations, is equal to the force of the bolt divided by KB plus KC. So we plug that into the previous equation, then we end up finding that the new force of the bolt is equal to the initial force of the bolt plus Fe times Kb over Kb plus Kc. And then similar idea for the load on the clamp, so how much clamping force there is in the joint. It's going to get reduced from its initial point by an amount proportional to the displacement and the stiffness. So again, that delta there still equal to Fe divided by Kb plus Kc. So we can plug that into this equation here, and we get the new clamping force in the bolt is equal to the initial amount minus Kc over Kb plus Kc Fe. So as we add additional load, we cause more stretching in the bolt, we cause less compression in the joint, and we can find the new forces in the joint and the forces in the bolt as a function of the initial load, the load that's applied, and then the ratios between those stiffness values there. So there's a few critical cases. If we have a pressure vessel, the point of a pressure vessel is to keep stuff contained inside the pressure vessel. So we don't want the joint to be opened. The joint will open if we get to a point where the clamping force is equal to 0. If Fc is equal to 0, then that is bad. So if we start here and then we apply enough force that this thing stretches out enough that the bolt stretches out enough that there's no more clamping force left in the joint, then we have a failure criteria. So we always want we want our Fc to be greater than 0. So if we want to prevent the opening of the joint, we need to make sure that our Fe is less than Fi times Kb plus Kc over Kc. If we do end up loading it past that opening point, then basically this is what happens with our relationship between our Fb. We get a relationship between Fb and Fc. So if we start for both the Fb and Fc, the force in the bolt and the force of compression in the joint, we start at our Fi, and then we load it up. Our Fc drops until it hits 0, and then past that it stays 0. For our Fb, the force in the bolt starts at Fi, it increases at a certain rate, and that rate is based upon the ratio between the stiffnesses of the bolt and the stiffness of the joint. And it increases until Fc drops to 0, and then after that, any additional force in the bolt, any additional force is just, well, after that point, any of the force in the bolt is equal to the force being applied, because the bolt is now the only thing that is, there's no other forces going on here. The compression's gone, so any additional increases in the force that's applied just cause more stretching in the bolt. Which will again eventually lead to failure of the bolt. So as for what those those elastic constants or stiffnesses are Kb and Kc. Well, again, we know from well, that's not even 331, that's 231, that the amount of displacement when you are stretching something with we're just stretching something with a constant cross section, that's going to be equal to the amount of displacement we get is equal to P times L divided by AE. So it's proportional to the amount of load, that's proportional to the initial length, and it is inversely proportional to the cross-sectional area and the stiffness of the material. So our K value, that's just P over the displacement. So the stiffness is equal to the amount of force you need to apply to get a certain amount of displacement. So that is equal to AE over L. So for the bolt, not too difficult to compute. One thing to keep in mind is when we're talking the A we want to use here is the A for the kind of the nominal size here. So the A of the bolt, because the stretching basically that's occurring is primarily going to be occurring in the non-threaded shank section of the bolt. So we got the shank section here, and then we got the threaded section here. So the threaded section has a smaller cross-sectional area, but bolts are going to be typically designed in order to have the threaded section only only near the ends of the bolts where you need it, where you need to apply the nut, and then the rest of it's going to be a smooth shaft. So the area that we're going to be using is for that calculation is kind of based upon the nominal area there. So again, pi d squared over 4. The E obviously is the Young's modulus for the material in question, and then the L is what we use. They tend to use G for that, for grip. It's basically just the thickness, the initial thickness of the joint. So how thick are the two things that you're clamping together? G, effective length, whatever you want to call it. And then similar idea for the joint stiffness. Got the Young's modulus, we've got the initial thickness, we've got this AC here. So that's the effective cross-sectional area of what you're joining together. And we'll talk about that, how to calculate that in a little bit. Sometimes it's obvious, sometimes it's not so obvious. That having been said, if you're bolting stuff together, you could be bolting things together that are of different materials, so they can have different thickness, different stiffnesses. So you just kind of need to figure out a way to combine those together. So it's just like this: 1 over the overall effective Kc is equal to 1 over the Kc for each individual section, add it all up. So you just use the G for each individual one. So say that's G1, and this is G2, and then you'd use E1 and E2, and then just continue to do that for each individual type of material that you're clamping together in this joint. So instances where this might occur would be like if you have some sort of, if you have a pressure vessel here and you've got a cover and a seal, and you may have a gasket in there, a gasket made of rubber or some other softer material that is there to deform into the space, make sure it's filling all the space and provide a nice seal. But the presence of that softer, more flexible gasket is greatly going to have a large impact upon the overall stiffness of the joint in question. So in general, obviously, if you're going to have a certain kind of, when you tighten stuff down, you're going to have kind of the forces that affect this tightening are going to be distributed throughout the joints that you're tightening. So basically, immediate, here up near the head, you're going to get kind of an immediate compression. Right next to it, there's no compression here, there's no compression here, so on and so forth. So you can't say that it's spread over the entire cross section of the materials being bolted together, because it's only kind of the little bit in between the bolts that are getting squeezed together. But it does spread a little bit. So it spreads out, so you get the compression kind of at the middle, and it kind of spreads out. So it kind of fills a certain volume. So it spreads out until it hits kind of a maximum point, and then, it stops spreading once it kind of hits the middle, and then goes back down. So between the head and the head of the bolt and the nut, you get the kind of like I guess it'd be kind of, you kind of got two lopped off cones stacked one on top of another, kind of looking like that. It's I guess looking something like that. So those two lopped off cones. So basically, what we do is we figure out that if we want to assign a value to this for the area of the compression, what we do is basically figure out what the average cross-sectional area is across this joint. So that can be figured out by based upon a combination of how big is the hole that the bolt needs to go through. So that's this D1 term here. How wide is the head of the bolt and the nut? I think we're assuming that that's the same thing. So that's that D2 term. And then this D3 term here is basically what's the maximum width that it spreads out to. And basically, kind of the way it works is that the spreading kind of happens at basically a 30-degree angle. So that's going to be about 30 degrees. So that distance there is going to be equal to this D2. You can mind this is the D2 plus 30 degrees times the grip there, the effective length there. So it spreads out to a certain amount. So the larger the the thicker the joint is, the more it's going to spread out. So you're going to get it over that effective volume. So if we want a bit of an exact value here, then you can do this calculation. Or if you want a reasonable approximation, I would generally go with the reasonable approximation. It's going to be roughly equal to our d squared term, whereas that d squared is just equal to, I'll just scroll up here again. Our D1 term should, we're assuming that we're not making the hole that the bolt's going into significantly larger than the hole, than the bolt itself. And then, I guess this D2 term here, basically the diameter of the head of the bolt and the nut. That's usually, typically speaking, about 1.5 times the D. So based upon those, the overall, we can get a reasonable approximation of the area, the kind of the effective area, cross-sectional area of the joint as a function of the size of the bolt and just the thickness of the joint. So essentially, we're going if we have a KC that's larger than our KB, then basically what we're going to do is we're going to tighten it up to a certain amount, and then when we increase the load, what's going to happen is that the amount of force, additional force in the bolt, is going to be less than the amount of change in the compression. Whereas the opposite occurs when you have Kc less than the Kb. And typically speaking, for most of the time, your Kc is going to be larger than your Kb, because the typically speaking, because your AC is going to be a lot larger than your your AC is typically going to be a lot larger than the cross-sectional area of your bolt is. There's a few cases where that may not be the case, like for example what I mentioned with the gaskets. Something like that could affect things. There's a few special cases that we can kind of determine. So if we have a soft body and a rigid bolt, so if we have a relatively thick, soft gasket here, then we can approximate that by just saying that, you know what, Kc, that's equal to 0. That's small enough that, it's not really, its stiffness relative to the bolt is low enough that we can just ignore it. So if that was the case, and we have a soft gasket steel bolt, you're going to tighten it up to a certain amount, and then any additional load applied is all going to go towards the bolt, whereas the compression in the joint, it's going to stay the same. So that means you tighten it up to a certain amount, and then as you apply additional load, the clamping force stays the same. So that gasket is just as capable of retaining the say the gas inside the pressure vessel as it was before it was loaded up. The other special case would be a rigid body and a soft bolt. So I don't know, some sort of metal that you're applying, and then you could have a rubberized portion of a bolt, or maybe it's just a plastic bolt. I don't know, whatever. So the opposite kind of occurs. What's going to happen here is that as you load up, your FB is going to stay the same, and all of the load is going to go towards decreasing the clamping of the joint, until you get to the point where there's no more clamping force left, and then after that, the load in the bolt starts to increase. So let's talk some failure criteria. So if we have a static loading situation, our failure criteria is going to be if the force in the bolt divided by the threaded cross-sectional area is less than or equal to the proof strength divided by our factor of safety, then we can kind of say, hey, or that can be used to compute our factor of safety. So again, just keeping in mind, this is what we use to compute our FB. And then our AT, looking up on the table, based upon the looking up on the table in juveniles. And then the proof load, again, also looked up on a different table in juveniles. So, for example, here's where we're looking up the tensile stress area. And here's where we're looking up the proof load based upon the grade and the diameter. So, that having been said, this failure criteria does not guarantee that we have enough clamping force. So we also need to check that everything's being clamped. So FC needs to be greater than 0. Therefore, FE needs to be less than FI times KB plus KC divided by KC. So as long as that is met and this is met, then we're not seeing failure in the bolt and we're not seeing opening of the joint. Now there may be some situations where where your design calls for a clamping force above a certain amount at all times. So it may not be that KC needs to be more than 0. It may mean that KC needs to be more than 100 newtons or 5,000 pounds, or I don't know, whatever it happens to be. You're just going to have to adjust your failure criteria appropriately. So as an example, if we have a bolted joint that has an external load of 8,000 pounds, got the bolt made of rolled steel, and if we are assuming that the elastic constant for the clamp or the joint is 6 times that of the bolt, which typically speaking is reasonable. It depends upon that'll depend upon to largely the diameter of the bolt we're talking about and the thickness of the material. But they're just saving us a calculation here. So KC is equal to 6KB. So what we need to determine here is what the initial tension load needs to be to prevent it when loaded. The loading, the clamping force, basically, if the tensile load on the bolt is 8.5 kips and the external load is 8 kips. And then whether or not this particular grade of bolt would be adequate. So let's start out with the first one. So again, the initial, this failure criteria that they specified for part A is that when loaded up to 8,000 pounds, the FC needs to be greater than 0. So when that's the case, FE needs to be less than FI times KB plus KC over KC. So here we're trying to solve for FI. So we'll just So in that instance, if we want the minimum Fi that we would need, that would be Fi would need to be equal to Fe times Kc divided by Kb plus Kc. Now keep in mind that we were given that the Kc is equal to 6 Kb. So our Fi needs to be equal to Fe times 6 Kc divided by, 6 Kb plus Kb plus 6 Kb. So our Fi needs to be equal to Fe times 6 over 7. Once we cancel out those Kb's. So our external load, or Fe, is equal to 8,000 pounds. So our initial tightening needs to be 8,000 pounds times 6 over 7. So that'll need to be 6.8 kips. So we got that. Okay, so part B here. The loading in the clamp. So what we're asking for here is Fc is equal to what? When the tensile load on the bolt is that, and the external load is 8,000 pounds. So again, we're still working with, we still know that in general, here, let's, I'll just, okay, so we know that our Fc is equal to our Fi minus that ratio times Fe. So B here, different. This is going to be a different kind of failure criteria than this one. Yeah, A and B are separate questions. So the Fi for this one needs to be based upon the condition that we were given here, that at that point when Fe is 8,000 pounds, the tension in the bolt needs to be equal to 8,500 pounds. So if we scroll up to, here, I can just take all of that. So just screen grab that. There we go. So we want to know what the FC is when the FB is equal to 8.5 kips and our FE is equal to 8 kips. So we just need to solve for what, come on. So in that condition, our Fi would be equal to our FB, 8.5, minus our FE, 8, times the KB over KB plus KC. So again, that there is 1 KB divided by 7 KB. Keeping in mind, yeah, this KC here, that's 6 KB. So this cancels out to 1 over 7. So our Fi, 8.5 kips minus 8 times 1 over 7. That gives us an Fi in that condition of 7.36 kips. So for that condition, we can figure out what our FC would be. So our FC, that's equal to Fi, 7.36 kips, minus Kc over Kb plus Kc times 8 kips for our Fe load. Again, Kc is 6 Kb in this situation, so that there resolves to 6 over 7. So our Fc is equal to 7.36 kip minus 6 over 7 times 8 kips. 7.36 minus 6 over 7 times 8. So in that situation, our Fc is equal to 1.4 kips. So again, that's our loading. Our loading situation of 8 kips is resulting in a 1.4 kip compressive load. The joints still being clamped together by 1.4 kips. Compare that to which is based upon having a higher initial load than what we calculated previously. We initially the first one, which is based upon the failure criteria of we need it to be not 0. That resulted in 6.8 kips as initial load. For this one, we're looking at it being more. We're looking at a higher initial load, resulting in a higher compressive residual force in the joint. So our Fc is going to be equal to that. And then the next question, for the conditions outlined in B, verify if the use of a 1/2 UNC grade 5 is adequate. So that's basically asking, is the bolt strong enough to withstand the forces applied in the bolt? So the force in the bolt is 8.5 kips. So how strong is a 1/2 UNC grade 5 bolt? Well, let's I think we can scroll up to yeah, okay, here we go. We can have a look at this table here, which was Again, taken from juveniles. So that's table 10.4. But here we've got the grade 5 half-inch. We'll have a proof load or proof load of 85 KSI. So 85 KSI is our SP. So I'm just going to write that down here. SP is equal to 85 KSI. And I guess I'll RFB in this situation is equal to 8.5 kips. So we got the proof load, and we also need what the thread area is. So for the coarse threads, let's see, that table doesn't quite go up to half. It was half, right? Yeah, half-inch UNC grade 5 bolt. So if we scroll up a bit more, just let me find. I know the table has it somewhere. Okay, so we look at this one here. Got the coarse threads UNC. We have a half-inch bolt here. Half-inch bolt will have UNC coarse. We'll have a tensile stress area of 0.1419 inches squared. .1419 inches squared. So what are we looking at here? So our failure criteria is based upon our proof strength here. So if we want to figure out what our safety factor is, again, just those things would be equal. So our safety factor, solving for our factor of safety, our factor of safety is going to be the proof strength divided by the force in the bolt times the AT. Yep. Let's copy that, scroll down a bit more. So plugging in what we have here, we've got our proof strength is 85 KSI. 85,000 pounds per inch squared times the AT, 0.1419 inches squared. Inches squared cancels out. And then divide by our FB, the load. That is 8,500 pounds. Pounds cancel out. That gives us a safety factor of, let's see, 85,000 times 0.1419 divided by 8,500. So that there gives us a safety factor of 1.419. Which, I mean, it's The question here did not specify a particular safety factor. So whether or not the use of that bolt is adequate will depend upon what sort of safety factor your particular project is going for. That might be fine. That might be grossly inadequate, depending upon the design criteria. But yeah, that'll be that. And yeah, see you. That's it for now.